Hello everyone. Can someone confirm if I am audible and is the slide visible? Okay. Okay. I think we can start today's session. So, good evening, everyone. My name is Arpit Bal. I am a PhD scholar at Department of Electrical Engineering, IIT Bombay, and I am the PMRF NPTEL-TA for this course, Digital IC Design. So far, we have. So this is our live session, the 7th live session, which will be related to the contents that were covered in week 7 of this course. Okay. So in week 1's live session, we covered numericals related to VTH variation and few numerical related to channel length modulation, that is one of the short channel effect, and we also tried solving a few questions related to drain current using the unified current equation. In week 2's live session, we also considered another short channel effect, that is DIBL. We solved a few problems related to junction capacitance, and we did some more numericals related to PMOS. In week 3's live session, we did numericals related to trip point and few numerical related to VIH and VIL that gave us a brief introduction about the noise margin, and we did some numerical on calculating the output for a given configuration. In week 4, we majorly concentrated on noise margin and Elmo delay. In week 5's live session, it was related to power calculation, that is mostly dynamic power, then delay, and one or two questions related to process variation. In week 6, we did few questions related to delay, electrical effort. So at that point, electrical effort was introduced, and how to draw CMOS schematic for a particular function, like how to design the PDN, and that's the pull down network and the pull up network. So we discussed that one, and then few questions related to capacitance calculation, and we also did few gate sizing related problems. So in week 7, what we are going to majorly look is the path delay calculation, delay optimization. Okay, then whatever efforts we learned, like logical effort, parasitic effort, and electrical effort. Okay, so we will have few numericals related to that. Okay, so without further ado, let's start today's session. Okay, so this is some basic generic guideline that we will come back to these points whenever it is necessary while solving the questions. Okay. Okay, so starting with the first question, what is the logical effort of a NAND 10 gate? Okay, so let us start with NAND 10. So NAND 10 refers to a 10 input NAND gate. Okay, so in the previous session we learned how to draw the schematic for a given function, right? So NAND will be, okay, so similarly it will go on. Okay, 10 PMOS in parallel. Okay, then we will have 10 NMOS in series. Okay, so before sizing it, the width will be 1 all for all the NMOS and 2 all for all the PMOS. Okay, but to ensure that the equivalent resistance is same as that of the reference inverter, so we will size the NMOS, okay, because this is present in a series format and the resistance will go on increasing otherwise. So now it is 10 R, so we need to ensure that the combined resistance is R, because of which each NMOS transistor will be scaled by a factor of 10. Okay, so if we scale any transistor by a factor of alpha, then the resistance get divided by that particular factor alpha. Okay, so this will be 10, this will be 10, everything will be 10 in this case. Okay, and we are supposed to calculate what is the logical effort. Okay, so let me call this gate A. Okay, so can someone tell me what will be the logical effort in this case?
4.
Okay, let me
4.
the students. Okay, yeah, so the logical effort will be 4. Okay, and how is it? It is 10 plus 2 divided by the logical effort of inverter, the reference inverter. Okay, so the reference inverter's logical effort will be, so this will be 2 and this will be 1, right? So 10 plus 2 by 2 plus 1, that is 12 by 3, that equals 4. Okay, so in the class there was one thing that sir mentioned, that if you are given an n input NAND gate, then you can directly write the logical effort, that is represented with G, okay, as n plus 2 by 3. Okay, so to make the calculations quicker, so you can directly use this formula, okay, But if you are stuck somewhere and if you have a doubt, then I'll suggest you to go with the basic, the first principles, like designing the entire circuit, okay, and then have the reference inverter, and then calculate the logical effect. Okay, so if you use the formula directly, so n represents the number of inputs, so we can write, so in this case it is 10, so 10 plus 2 by 3, that will be again 4. Okay, so is everyone clear with this, or is there any doubt? Clear. Okay,
Suppose when add 12 means just the n is equal to just 12.
correct.
Okay.
Okay, so okay, there is one message. Okay, yeah. Okay, so just like we did for NAND, so let's do the same thing for NOR gate. Okay, so can someone tell me what will be the structure for NOR 10?
Parallel connection for NMOS and series connection for PMOS.
Yeah. Okay, so we will have similarly 10 such connections for PMOS, and we'll have 10 such connections for NMOS. Okay, and let me call this gate as gate A. So can someone tell me what will be the logical effort in this case?
7.
Okay, let's see. Okay, so initially we will have, before sizing, we will have NMOS all the widths as 1 and PMOS all the widths as 2. Okay, but after sizing, the PMOS is going to be 20 because we will multiply the width by a factor of 10 so as to decrease the resistance by a factor of 10. Okay, so we will have G equals to 20 plus 1 by 3. So 3 is the reference inverter's logical effort. Okay, so we will be arriving at this number as 7. Okay, so just like for the NAND case, an n input NAND, you can find out the logical effort by using n plus 2 by 3. Similarly, for NOR case, you can figure out the logical effort by this formula. G equals 2n plus 1 by 3. Okay, so where n represents the number of inputs. Okay, so if I substitute, so this is only applicable for NOR. So do not get confused between which equation to be used in NOR and which to be used in NAND. So yeah, so if I substitute 10 here, so it will be again the same thing, that is 7. Okay. So just to make the calculations quicker, you can use this formula. Okay, so is there any doubt? Is everyone clear? Okay. Okay, moving on to the next question. Okay, parasitic effort of a NAND 6 gate. Okay, so we have to figure out what is going to be the parasitic effort of a NAND 6. Okay, and then I will tell you the relevance of parasitic effort and the logical effort part. Okay, so for NAND 6, so you can have, so you will have 6 PMOS in parallel and 6 NMOS in series. Okay, so when you scale the NMOS, it will be 6 and the PMOS won't need any scaling. So you have 2 into 6 plus 6 by 3. So this 6 is from the NMOS side, okay, and this 2 into 6 is from the PMOS side. You will have total 6 PMOS, okay, and so I'm talking about this capacitance, okay. So you will have 6 PMOS and the width of each PMOS is 2, okay, and this 3 is from the inverter, the reference inverter. Okay, so you have this thing as 3. So we arrive at 12 plus 6 by 3, that is 6. Okay, so just like we did for NAND 10 and NOR 10, that we had a formula for getting the parasitic effort as well. You can directly write that the parasitic effort of a NAND gate is N, where N represents the number of inputs. Okay, so so intuitively, what is a parasitic effort and what is a logical effort? So logical effort is basically the capacitive loading that a particular gate puts on the previous gate, okay, and parasitic effort is the capacitive loading that the gate puts on itself. Okay, so that's the intuition behind what is parasitic effort and what is the logical effort part. Okay, yeah, so what is the parasitic effort of a NOR 6 gate?
6.
Yeah. Yeah, Sanjay. You have a question?
No, sir.
Okay. Okay, so this is our NOR 6 gate, and then we will have six NMOS in parallel. Before sizing, it will be 1 1. This is 2 2. Because it's a NOR 6, so it will be 12. Okay, and at this node, what will be the capacitance? That will be 12 plus 6 whole divided by 3, that is 6. That's the answer. Okay, and similarly, so here also the parasitic effort is equal to N, where N is the number of input. Okay, so is everyone clear till this part? So question 1, 2, 3, 4 were pretty straightforward questions. So is everyone clear with this? Okay. Okay, moving on to question 5. Take a NOR 3 gate and tie all inputs together. Okay, so we will go step by step. We'll first draw the NOR 3 gate. Okay. Okay, and what is mentioned? And tie all inputs together. Okay, so I'm tying all the inputs together. What is the logical effort for rise of this inverter? Okay, so can someone tell me if this is actually an inverter? If yes, can someone just try to prove it? Yeah.
If the input is 1, then all the NMOS are turned on.
Okay.
So output is directly connected to ground.
Okay.
And in similar cases, if the input is 0, all the PMOS are turned on and the output is connected to VDD.
Okay. Just a minute. Yeah. Okay. So, yeah, that explanation is quite correct. But to be in a very generic manner, so what I can say is, if it's an OR3 gate, okay, so if I put all these things connected together, and if I am applying an input A, so it will be A plus A whole bar. Okay, that is going to be A bar. Right. So it means if I am giving an input A, my output is going to be A bar. Okay. So using equations, so things will be made simpler in a way that, so whatever combination is given to you. So this one is a very straightforward one because it says NOR 3. Okay. Let us say you have a very complicated gate, okay, with a bunch of inputs. Then to observe that it is an inverter, if you go on observing, if I feed a 1, then the output is 0. If I feed a 0, then the output is 1. It is quite complicated. So better you can directly use the equations and see if you apply an input X and you are getting an output X bar. Okay, then that will be an inverter. Okay. Yeah, so moving back to the question, what is the logical effort for rise of this inverter? Okay, can someone answer this? So take a moment. So whatever 4 questions we solved so far, so this is related to that. So can someone try to answer this?
Sir, is it 7?
Yeah, it is 7 and
7.
Yes, correct.
21/3.
Yeah, and how did you arrive at this number?
Sir, all PMOS are size 6, so adding all that, and NMOS is size 1. So that 18 plus
21C.
3.
21C divided by standard reference inverters input capacitance 3C, we get 7.
Okay, yeah, that's correct. Okay, but okay, there is one more part to this question. So it is asked that what is the logical effort for rise of this inverter? So it is asking for the rise part. So will it matter if I am considering rise or fall in this case?
No, because the input will be input load, the input capacitance which is presented at load to the previous stage will be due to both PMOS and NMOS.
Yeah.
Irrespective of whether it is rise or fall.
Okay, yeah. Yeah, so the thing is, so I just need to calculate the G. Okay, so in the lectures you must have seen that it was calculated for G rise and G fall. Okay, and whenever G rise or G fall was taken, so it was taken with respect to a reference inverter. Okay, so for G rise we used to take the same sort of PMOS as the reference inverter, and for G fall we used to take the same sort of NMOS for the reference inverter. Okay, so in this case, because so both of them are having symmetric swing, so the G rise and G fall will be same, and that is going to be 6 into 3. So this is 111, this is 222, that will be 666. Okay, so because all 3 of them are shorted, the inputs are shorted, so it is 6 into 3 plus 3 whole divided by 3. That is going to be Y6. Okay, so these PMOS are connected in series, right? Okay, so if they are connected in series, then the equivalent resistance will be 3 times R. So I need to size each MOS such that the resistance offered by each PMOS is going to be R by 3. So the equivalent resistance will be R. And if I need to reduce the resistance by 3, it means I need to size the transistor by 3 times. So if earlier it was 2, now it will be 6. Okay. Okay, so this is 21 by 3, that is equal to 7.
Sir, can we explain one more time for G rise and G fall?
Yeah, so whenever we are taking that G rise and G fall, so it was covered in the high skew, yeah, I think it was covered in the high skew lecture, the skew transistor lecture, I guess. Okay, so in that case, what we used to do is, let's say we are talking about the G rise. Okay, so whenever you consider the G rise part, you have to compare with the inverter, reference inverter. Just a minute, someone is trying to join. Yeah, okay, so we need to compare it with the reference inverter, which is having symmetric swing. Okay, so it means that if I am like in this case, it is going to be 2-1. But in the high skew cases, like high skew or low skew case, so we used to reduce the width of the NMOS by some quantity and width of PMOS by some quantity, right?
Yes, sir.
Yeah, so in those cases the comparison was also a bit different.
Okay, sir.
Okay, so it was like yeah, the comparison was different because so let's say PMOS I am taking 1 and NMOS I am taking 1. Okay, and I am considering the G rise. Okay, in that case the reference inverter's PMOS is going to have the same width 1. Okay, but to make it symmetric, the width of NMOS should be half.
Yes, sir.
Okay, so yeah, so that was being considered, but in this case it is not applicable because here we can see directly that the PMOS equivalent is also R and the reference inverter's PMOS is also R. So we need not make that skewness present
Sir,
here.
in this case, we are using the unskew inverter, that means
Correct.
2 and 1.
Yeah, yes, yeah.
Because nothing is mentioned in
Yeah.
to use the high skew or low skew.
Yes, correct. And because
So
of
if
this,
sir for low skew you are saying that 1 and 1 by 2 for PMOS and NMOS respectively, then for the G rise 1 by 3. Okay, sir. Okay, sir.
Yeah. Okay. So similarly, try to attempt. Yeah, Ravi.
So in question number 1 and 2, in large scale effort, we can take in parallel connection, we can take one of the NMOS values, sir.
Sorry, can you repeat?
So in question number 1 and question number 2, in parallel connection, we can take any one of the width of the any one of the transistor. That's
Yes.
the two value. But here in logical effort, right, in fifth question, why you can take all the values of parallel connections?
Yes, because it is mentioned that tie all inputs together. So it means, so these are not separate inputs, separate distinct
Okay, sir.
inputs. It's the same input.
Okay, sir.
Okay. Okay. Same. Yeah.
5.
Sorry.
5.
Oh, okay, okay. You are telling the answer. Okay. Yeah.
Yeah, I'm telling the logical.
Yeah. That's correct. Okay. So I'll request others to try this one as well. Okay. So basically, you need to do the same thing that we did for the NOR case. In this case, we just need to. Yeah, my drawing is a bit bad, so. Okay, then again you sort all the inputs. Okay, and after sorting all the inputs, so this one will be actually upsized to 3, and the PMOS side will still remain as 2. Okay, so we have G equals 6 plus 9 by 3, that is 15 by 3, that is 5. Is everyone clear with this? And again, because it is unskewed, then the logical effort for fall of this inverter will be same as the rise. Okay, so moving on to this question. Okay, I'll probably need another page, so let me add another slide here. Okay, so in this question we have to calculate the optimum stage effort for the gates of the circuit shown below. All gates are sized for equal rise and fall delay, and the input inverter presents a capacitance of 2 lambda of width, and the output capacitance is equal to 243 lambda by 8 of width. Okay, so I'll mention like how this information present here, it is not much different than what we conventionally do. Okay, so first thing first, so we will try to calculate the logical effort of each of these gates. Okay, so because we are supposed to find the optimum stage effort, that is the F hat. Okay, so first that we will calculate is the logical effort for the individual this thing. Okay, so we need to calculate F opt, okay, that is G H to the power 1 by n. Okay, so let me call this as I1, I2, I3, I4. Okay, we don't need H for this one. So
Is the answer 3?
let's see, I haven't done the complete calculation. So let's start it gate by gate. So can someone tell me what is the G for I1?
1.
For I2?
4 by 3.
Okay, so one question here. So does it do I need to know the drive strength here for I1 or I2 for calculating the G?
No.
No, sir.
Okay, and why is it so?
Independent.
Because when we divide the input capacitance, we take reference inverter of same drive strength, so
Correct.
they'll cancel out.
Yeah, so for G it won't matter what is the drive strength. Okay, similarly for I3,
2.
okay, for I4,
2.
okay. So is everyone clear with how we arrived at the G values for all the gates? Is there any doubt? Okay, so now we will find out the path logical effort, that is product of all individual path efforts. Okay, that is 1 into 4 by 3 into 2 into 2. That is 16 by 3. Okay, is this part clear? Next, we need to find out H. And H, we know that, so whatever is the node capacitance present here, so we can assign some variables to it, but that is not needed, because when we take product of all the node capacitance, means all electrical efforts, so everything will get cancelled out except CL by C0, where CL is the final load, C0 is the initial. Okay, so that will be 243 lambda by 8 divided by C0, that is 2 lambda. Okay, so our GH becomes 16 by 3 into 243 by 8.
16.
243 by 16. So our P will be, so so our F opt will be GH to the power 1 by N, and our N was the number of stages, that was 4. Okay, so we have 16 into 3,
We can just cancel out 16 and 16. 81 times is 2.
This is 81. Yeah. So this is 81 to the power 1 by 4. That is 3. Yeah. 80.9 is not the correct answer. It should be 3. Okay. So 3 is the optimum stage effort. The product of GH is 81, but F opt is GH to the power 1 by N. So N is the number of stages, and it will be 81 to the power 1 by 4. Okay, so I'll take a pause here. Oh shit. Yeah, so I'll take a pause here and let me know if anyone has any doubt in this question before proceeding with the next question. So next question is a bit time taking. So yeah, so if anyone has any doubt in this question, let me know. Okay, so we were supposed to calculate the optimum stage effort, where N is the number of stages. Okay, and optimum stage effort is given by this equation, where G represents the path logical effort. Okay, and G is defined as product of individual logic efforts. Okay, and H represents the path electrical effort. So H also represents product of individual electrical efforts, but the moment you take the product of individual electrical efforts, so you end up with C out, that is the C load, by C0. So C0 is the input capacitance that was mentioned to you. Okay, so the first thing that we need to find out is GK. Okay, that is the logical effort for individual gates. So we name the gates as I1, I2, I3, I4. Okay, and we figure out the logical efforts for each of these gates. For inverter, it is 1. Okay, for a 2 input NAND gate, it is 4 by 3. For a 4 input NAND gate, it is 2. Okay, and similarly I4 is also a 4 input NAND gate, that is 2. Then we figure out what is the path logical effort, that is product of all these individual logical efforts. That is 1 into 4 by 3 into 2 into 2, that is 16 by 3. how to. Okay, so are you talking about this one, the NAND gate? Okay, so G is equal to n plus 2 by 3. Okay, so that was the formula that I mentioned in the beginning. So n is 4 here because it's a 4 input NAND. 4 plus 2 by 3, that is 6 by 3 is 2. Is that clear? Okay.
Sir, one more question.
Yeah.
Sir, in this case, we are directly find out the electrical effort H by CL by C naught. So similar type of explanation sir also did in his lecture, that if the every gate I1, I2, I3, I4 some scale factor 2, 4 something, 64 something like that. For finding the electrical effort, sir find all the CL and CN of all the gates I1, I2, I3. So for I1, I2, I3, all the gates, at first find out the CN value, but for the CL value, say just do the CL value of that gate of the CN value of the next gate, something like that. Just copy it.
No, I didn't get this one. Can you repeat once?
Like sir, for CL value for load capacitance of the inverter I1, say just copy the CN value of the I2 gate.
Okay. Yes.
Because
Yes.
obviously
Yes.
it is
Yes.
a function of next input impedance
Correct.
of the next inverter,
Yes.
next gate.
Yes.
I understand, but for the first inverter, what it has also its output impedance or
Parasitic.
output capacitance, right?
Yeah. Yeah.
So sir, then the total capacitance would be lumped with the parallel, they would be adding, right?
Yeah. But so we are assuming that it is lumped in X1. That X1 is the dominant one.
Okay.
Okay.
That means its own output capacitance won't get added.
No. Means that's just an assumption to simplify our solution.
I mean, sir, suppose sir, first I1 inverter, it has input
It
capacity,
will have
input
its
gate
own
capacity is
parasitics.
3C,
Yeah.
and output capacitance also is 3C. For the next I2 gate, it is having its input capacitance of for a single input, it's a 2 input NAND gate, so 2, so it will be 4C.
Yeah, I understand that point, but if you see, like we have written the delay in the form of GH plus P, right?
Yes, sir.
But the delay that we obtained from Elmore delay is different. Okay, so this is
Yes.
actually a bit of simplification, so we use several layers of simplification to ease out our calculation for understanding what is going to be the drive strength or what is the optimum number of gates that we need to use. Okay, so this is also another simplification that has been used, but yes, whatever point you mentioned, yeah, that is correct. Like this inverter is present here and it will also have its own parasitics that will act as a load. Okay, but yeah, for simplification purpose we are not going to consider that.
No,
So
sir
we are
said
not going to
that
consider
its
its
own
own.
parasitic will not be considered as load because we
Yeah.
are including it in its own parasitic effort, right? So only G
Yeah,
and H
that-
will.
Correct. So that parasitic effort term is already kept separate, like GH plus P.
Yeah,
So-
it's already captured. So we are not approximating that like electrical effort. It's
Yeah.
given as load by input capacitance, right?
Yes,
So
yes.
we are not making any approximations there because
Yeah,
the
but it
output
will
of the
otherwise-
gate is already considered in the parasitic effort itself, right?
Yeah, correct.
Okay, sir, got it. For that means we have to consider its next input impedance as its previous load capacitance. Just copy, because already added the parasitics in the PE side.
Yeah.
Okay, sir, got it.
Okay. Oh, wait. Okay. So the next question is, Okay, so we have this configuration given to us, and what we need to find out is okay, and then okay, so these are the two things that we need to calculate. Okay, let me add one slide. I'll add two slides instead. Okay, so let me call this one as gate I1, I2, I3, I4, I5. Okay, let me call this one as X1, this as X2, this as X3, this one as X4. Okay, so first thing we need to do is we need to construct the table. So where G represents your logical effort, H represents electrical effort, and P represents parasitic effort. Okay, so yeah, so for I1, what is going to be the G?
One.
And what is H?
1.
X1.
X1.
And what is P?
1.
Correct. Similarly for I2,
5/3.
yeah.
5/3.
For I2, what is the H?
X2 by
X2
X1.
by X1.
What is the P?
3.
3.
Yeah. Similarly for I3, what is the G, H and P?
5/3, X3 by X2 and 2.
For I4,
4/3, X4 by X3 and 2.
and for I5,
150 by X4 and 1.
okay. So we have the individual logical effort, electrical effort and parasitic effort. Now we need to find out what is the path logical effort, that is the product of all the individual logical effort. Okay. This is 100 by 27. This is CL by C naught, that is 50x, this one, by C naught, that is 1. Okay, and our F is G into H, that is 100 by 27 into H, that is 50. Okay, so optimal stage effort is equal to, can someone calculate this?
2.84.
Okay, okay, so what is the minimum delay? Okay, so we have P here, so let's calculate the P first. That is going to be summation of Pi 1 plus 3 plus 2 plus 2 plus 1, that is 3 3 3, that is 9.
23.2
Okay,
minimum delay.
okay, so the n is 5 into f to the power 1 by n. So f to the power,
2.84.
yeah, it was 2.84 plus p, we just now calculated, it was 9. Okay, so this is going to be 23.21. Okay, is everyone clear till this part? How did we calculate the minimum delay?
Yes.
Okay, does anyone have any doubt? So I'll pause here for 1 minute. Can you tell how to calculate the parasitic delay once? Yeah, okay. So parasitic delay is basically you observe the output node, whatever the total capacitance is present there, and then divide it by the reference inverter. So let me try to do this for I2, let's say. Okay, I2 parasitic delay. Okay, so I2 was a NAND 3. Right, so it means we will have 3 PMOS in parallel and 3 NMOS in series. Okay, so before sizing it will be 111 and 222. Because 3 NMOS are in series, so I'll scale it by a factor of 3. So what is going to be my capacitance at this node? It is going to be 3 from the NMOS plus 2 into 3 from the PMOS. Okay, that is 3 plus 6 is equal to 9C. Okay, then to calculate the parasitic effort, I will divide this 9C by the inverter's output parasitic, that is 3C. So it will be 3. Is that clear? Rishendra?
Yes, sir.
Okay. Okay, so does anyone have any other doubt in? Okay, so we just completed part 2. We will do the part 1 now. So does anyone have any other doubt in whatever calculations we did? Okay. Is everyone clear with this part? Yeah, so I'll revisit all the problems again, but let us solve question 8 first. So there are few more steps left to calculate the drive strength of each gate. So in question 8, this part, is everyone clear?
Yes.
Okay. Okay, so this was the minimum delay. Okay, and to calculate the individual the drive strength for each of the cases, we need to figure out what is going to be so each FK, so each stage effort, it should be equal to the optimal stage effort that is equal to 2.84 that we obtained earlier. Okay. Is this drive strength of each gate? Okay, someone has already calculated it. Great. Okay, so Fi1 will represent the first gate I1. Okay, so G1 H1. So F is basically G into H. Okay, so what is G1 H1 for the first gate? That is X1. Okay, and it should be equal to 2.84. This implies X1 is equal to 2.84. Okay, similarly Fi2, okay, that is G2H2. So can someone tell me what is Fi2?
2.84.
No, sorry, means the equation for Fi2. That is G2 into H2. So G2 is 5 by 3 into H2 is X2 by X1. Okay, that is equals to 2.84. This implies, so from whatever value I obtained for X1 in the above case, I'll substitute that here. So I'll have X2 equals 2.84 into 2.84 into 3 by 5. That is equal to 4.84. Okay, similarly I'll do for Fi3, that is G3H3. Okay, and my G3 was also 5 by 3 and H3 was X3 by X2 is equal to 2.84. Substituting the value of X2 here, I'll have X3 is equal to 8.247. Okay, is this part clear? Okay, the next thing that we need to calculate is Fi4. Yeah, that is G4H4. That equals 4 by 3 into X4 by X3 equals 2.84. This implies, so X3 we obtained in the previous case as 8.247. So our X4 will be 2.84 into 3 into 8.247 by 4. That is equals to 17.567. Okay, so we have all the variables available with us, but still to confirm that the calculation is correct, we will also calculate Fi5, that is 50 by X4, that is equals to 2.84. So whatever value we obtained for X4 should be in agreement with this value. Only then our calculation is correct. Otherwise we need to recalculate things. So this will be X4 equals to 17.6. So these two answers are almost same. Okay, so it means our calculation is correct. Is everyone clear with this? Yeah, okay, so is everyone clear with this question? Is there any doubt? Yes. So whatever delay that was obtained, you where did that question go? Multiply the delay by 3RC to get the actual delay. Why 3RC?
Sir, because the delay we calculated was the
Relative.
normalized delay.
Yes, yeah. But 3RC, I didn't get that part.
3RC is the delay of an inverter.
But we don't need to do it here.
Yeah, we don't need to. But why exactly 3RC? That thing I didn't get.
Sir,
Because when we found out the normalized delay, we divided the actual delay by the delay of the inverter.
Correct,
So when we
but-
multiply it, we
yeah.
get the actual delay.
Oh, okay. But why is the R coming in picture? Wait, will it be 3RC?
Sir, it's Elmore delay.
Oh, no. You don't need to do that.
Okay, sir.
Okay, yeah. Okay, any more questions? Drive strength of each gate. Okay, so drive strength of each gate, it actually means like whatever gate you are using. Let's say an inverter. Okay, so a normal inverter would have one NMOS width and two PMOS width, right? So if I say drive strength of X, it means the NMOS width is X times and PMOS width is again X times. So it will be 2X by 1X, means 2X for PMOS and 1X for NMOS. That will be the drive strength for that gate. Okay, there is one more question. 2 point. Achha, this is the answer. Okay, notice. Yeah, we will revisit that particular problem again. Parasitic delay. Okay, it was mentioned. Yeah, is there any other doubt for this question?
These are not the actual capacitances, right? These are like in terms of X. We need to multiply by them 3C.
Yes. So to get the absolute value, you need to multiply it by 3C. And if you further want to go on and figure out the width of the individual transistors as well, you can do that. Okay, so every calculation that we did today, so it was all relative and like it was normalized. It was not the absolute value. Okay, and to
Sir, multiply by 3C, why?
Because see, here we have divided everything with 3C, right? So 3C to make it normalized with respect to the inverters.
Oh, okay.
Is it possible to calculate min delay without using formula? Which formula? Can you mention that one? That GH plus P?
Sir, n into f power 1 by n plus p, that formula. Minimum delay.
Okay, so yes, if the gates are properly sized, then you can directly figure out the minimum delay by GH plus P itself. But here we need to first figure out what is the optimal stage effort, and based on that we are doing it. So that's why we need to do the calculation.
Okay.
Okay, is there any other question for this last question? Okay, let us revisit one question that someone mentioned. Um, inverter's logical effort for rise problem. Okay, yeah. So, is this the question that you were asking about, Shilpa? Okay. Yeah, so basically in this case it is mentioned that we need to tie all the inputs together. So here there is no other input apart from, let's say, A. Okay, because A, B, C, whatever input gates were present, we have shorted them. Yeah, because there is no skewed gate present here, right? How to find least logical effort in CMOS circuit? What do you mean by least logical effort?
Sir, in assignment, they gave an equation.
Hmm.
From that equation, we need to find the transistor with least logical effort.
Okay, I'm not aware about the assignment part, so
That was last day assignment.
oh, okay. But I can't answer that. But if you were asked for choosing between inverters which have the least logical effort, then you can find out the logical efforts from PMOS width and like adding the gate capacitance, right? And then comparing them. I guess I'm not sure. I haven't seen the assignment questions.
Sir, for any complex logic circuit, there are so many inputs. So for different inputs, the logical input can be different, right?
But whenever you are using a CMOS, so it means that you will have like whatever NMOS you have, so the dual of that will be present in the PMOS side.
No, sir. Just like for the previous assignment question, just like the for finding out the critical path delay, some NMOS sizing having 1.5, some having 2. So in
Yes.
that case, PMOS is
Yes,
having
yes.
different A input capacitance
Yes.
and NMOS.
Yeah, that is asymmetric input. So in case of asymmetric gates, that is possible. But in most of the designs that we did today, or like if you see, those are symmetric. So yeah, if you come across a case which is having asymmetric inputs, then sure, you can. You need to find the logical effort for all the inputs differently.
Yes, sir, because in complex gates we have to do for the critical delay because we have to minimize the area.
Not exactly in complex gates. So you can have a very complicated circuit, okay, CMOS circuit, but all the inputs can have same logical effort. Okay, but if let's say some inputs are given priority over the others, that some kind of asymmetricity is introduced there, in that case every input will have a different logical effort. Otherwise every input will be same, even if it is a very complicated gate.
Okay, sir.
Okay, so unless you see that asymmetric behavior, okay, like you remember the example that sir gave of reset and a signal arriving at the input of a NAND gate, right?
Yes, sir.
Yeah, so in that case asymmetricity was done. So if it is done knowingly, then deliberately, then yeah, true.
Say in earlier weeks, in live session of yours, some of the question is like the critical path relay find using the sizes, using the critical path relay. The one NMOS is having the 1.5. I said it was 2. Then you corrected me because it should be the minimum area.
Oh, okay. Yeah. That is not related to critical delay thing. It was that whatever sizes we were choosing, it should be such that the total sum of all the widths, it is minimum. So at that time we were like choosing.
Yes, sir. At that time, you said that first find out the sizes using
Yes.
the critical path relay, because what is the critical path relay? We have to sizes first.
Yeah, so critical path for rise and fall. Yeah, okay.
Yes.
Okay, let's revisit whatever we did. So these were all the set of questions that I planned to cover today, and yeah, so let us revisit whatever we discussed today. So first thing that we discussed was related to logical effort of a NAND 10 gate, 10 input NAND gate, and we can directly use this formula, or else we can go by drawing the schematic and then figuring out what is the logical effort. So for this formula is applicable for a n input NAND gate logical effort. Okay. Similarly, next we were supposed to find out what is the logical effort of a NOR 10 gate, and we can directly use this formula to figure out what is the logical effort. Okay. Next question was related to figuring out the parasitic effort of a NAND 6 gate, and for an n input NAND gate, the parasitic effort is basically equals to n, where n is the number of inputs. Okay, so the same thing we arrived here as well, 6.
Sir, in the last question, if you want to find out the electrical effort, then for the first question, then H is like 2 into 10C plus 10C, that means 30C on CL load capacitance for first question.
CL, okay, yeah. So if no load is given, then you are assuming that the drain capacitance is the load capacitance, is it?
Yes, the total diffusion capacitance. Actually.
Okay, yeah.
So it will be 36. If we want to find out the electrical effort, then
CL by CO.
Input impedance. Yes, for input impedance, we have to calculate for single input A or B.
Yeah, for single like input.
Okay.
Okay, so the next question was related to an OR3 gate in which all the inputs are tied together, and we were supposed to figure out what is the logical effort of this inverter. And because there is no skewness present here, so the rise and fall time will be the rise and fall logical effort will be same. Okay. Next was we were given an AND 3 gate, and we were supposed to tie all the inputs together, similar to the previous question. And even in this question there was no skewness mentioned, so we can figure out what is going to be the logical effort of this inverter. Okay, then we were given a circuit and we were supposed to figure out the optimum stage effort for the gates. Okay, so the F opt is GH times 1 by GH power 1 by n, where G is the path logical effort and H is the path electrical effort. So path electrical effort is your CL by C naught. In this case it was 243 lambda by 8 divided by 2 lambda. Okay, and we first calculate the individual G values. After figuring out the individual G values, we take the product of those individual G values to get the path logical effort. Okay, after finding out the path logical and path electrical effort, we figure out what is the F opt. Okay, that is the optimum stage effort. So that will be GH to the power 1 by n, where n is the number of stages. So in our case the number of stages was 4, So 81 to the power 1 by 4, that equals 3. Okay. So the next question, we were supposed to calculate the minimum delay and the drive strength of each gate. And so in this question, first we need to figure out what is the individual effort, individual logical effort, and the path electrical effort, that is going to be CL by C out. And we need to calculate what is the optimal stage effort first. Okay, so the optimal stage effort is product of G into H, that is to the power 1 by 5, that is the number of stages. In this question, the number of stages were 5, so we obtain the optimal stage effort is 2.84. Then we also calculate the parasitic effort, the parasitic path effort for this one, that is summation of all the parasitic efforts, that is 1 plus 3 plus 2 plus 2 plus 1, that is 9. Okay, then we figure out what is the minimum delay. So the minimum delay is n times f to the power 1 by n plus p. Okay, the p we found out to be 9, and n was 5 into f power 1 by n, that was 2.84. Okay, so the minimum delay is 23.21. Okay, after finding out the minimum delay, we also know the optimal stage effort. So to figure out the variables x1, x2, x3 and x4, so we know that each stage effort should be equal to the optimal stage effort for minimum delay. So fi1 we equate with g1 h1 equals 2.84. okay, so we obtain x1 is equal to 2.84. Similarly, we do the same thing with fi2, fi3, fi4. So we could have stopped at fi4 itself, but whenever you are doing such huge calculations, there is a probability that you can I mean, by mistake you can arrive at a wrong solution. So to have a proper verification, you can also go and check the last stage the variable value. If it matches with whatever variable value you obtained previously, okay, then it means whatever you have solved is correct. Okay, so this is what I planned for today. If anyone has any doubt, please let me know. Okay, does anyone have any doubt?
Sir, can you explain us one problem, a small problem of G rise and G fall with unskew or high skew or low skew? Small.
Okay, I
problem.
haven't prepared any question, but should I repeat the example that was taught in class?
Yes, sir.
Okay, so maybe I'll try with the high skew one. I'll add a slide. Okay, so let us try out one thing from, this is from low skew. Okay. Okay, so in a low skew gate, let's say this is my inverter, okay, and I want to prefer my falling edge over the rising edge. Okay, then what I will do is I'll keep the PMOS width and NMOS width as 1, 1. Okay.
Okay, sir.
So in usual cases, what would have happened is I would have kept my PMOS width as 2 and NMOS width as 1. Okay, but in this case I am going to do that PMOS width is 1 and NMOS width is 1. So it will mean that I am making my NMOS stronger than my PMOS.
Yes, sir.
Okay, so if let's say in this case I want to figure out what is going to be my what is GPD. Okay, that is pull down logical effort, then it means I need to take a reference inverter which is going to have symmetric swing, and the width value will be same as width of the NMOS value will be same as that of my let me call it DUT inverter. Okay, so if my NMOS is 1 and if I want symmetric swing, what should be my PMOS width?
So 2.
Yeah. Okay, so now if you compute the gate capacitance in this case, what will be the gate capacitance here?
2C.
Yeah, and what will be the gate capacitance here?
3C.
Okay, so now what will be my GPD?
2/3.
Yeah. Okay, this is for the pull down part. Now let me consider the pull up part.
So that means reference part is the unskewed part.
Yes, so reference part should be having symmetric swing and width same as that of whatever DUT you took.
That is my basic size 1 reference inverter, 2-1.
Yeah.
Unskewed part. Okay, sir.
Not necessarily 2-1, it could have been different. So it would have depended on my NMOS width. Because my NMOS width was same, so that's why my inverter's NMOS width also I kept as 1.
Oh, okay, sir.
Okay, so okay, I think GPU will clarify that point. So while doing for GPU, so can you tell me what will be my reference inverter?
So then my PMOS should have same size, that means 1, right?
Yes. And what will be my NMOS value if I want to have symmetric swing?
Just half power.
Yeah. Okay, so in this case, what will be my gate capacitance?
3/2C.
Okay, 3/2C. And the DUT's capacitance is 2C. So what will be my GPU?
4C/3.
Okay.
Yes, sir.
So it means like I'm decreasing my GPD, but I'm increasing my GPU. The pull up part I am increasing, but the pull down part I am decreasing because I want to give preference to the pull down logic more.
Okay, sir.
Okay. Yeah. Okay. Is there any other question?
Sir, could you please add this in your slide?
Yeah.
For upload?
Yeah. So it will be uploaded because whatever I'm writing here, so I upload the same thing on the deck.
Okay, sir.
Yeah. Okay. Is there any other question? There is one question.
Sir, this GPD is G-fold, no?
Sorry?
GPD is G-fold.
Yes, yes. PD, from PD I mean pull down.
Pull down, okay, for
Yeah.
fold. Okay, sir.
Okay. Is there any other question?
Sir,
Yeah.
sir, why can't we put 3 by 2 by 3 for G bull-ups?
G pull up 3 by 2 by 3. No, that's the reference inverter. So this thing is the reference inverter, right? So this is our DUT. Okay, and we are just changing which reference inverter to take when. Is that clear?
Sir, can you say one more time?
Yeah, so whatever I have drawn here, it is basically the reference inverter, what we need to do. Okay, so our actual circuit is this one, for which we need to calculate the GPU and GPD. Okay, but we anyway normalize it with respect to an inverter, right? So with respect to whatever we need to normalize, so this is this one, A or B. So these are actually the reference inverters. Okay. Okay, then there is another question. How in GPU it is 3 by 2? Yeah, it's because the PMOS size is 1 and the NMOS size is 1 by 2, right? So that's why it is 1 plus 1 by 2, 3 by 2. Okay, is there any other question? So I'll upload the recorded this particular recording and on the YouTube channel, and it will be available by 8:30. So I'll also upload the slides including this part, whatever GPD, the skewness part you had a question, and yeah. So if anyone has any other question, let me know. Else we can wrap up today's session. Thanks for joining, everyone.
Thank you, sir.
Yeah, thanks. Okay, I'll still be around here. If anyone has any question, then they can let me know. Yeah, thanks. Rishendra, do you have any doubt?
Sir, if there is time at the end, can you please go through second order effects, sir?
Okay, second order effect. Wait, I need to open that
Like
slide.
subthreshold swing.
Okay, so which second order effect? Do you have any effect in particular that you want to know?
Sir, I would like to know about subthreshold swing and velocity saturations.
Subthreshold conduction.
Swing, sir, subthreshold swing. Subthreshold slopes.
Subthreshold slope. Okay. I think that was covered
Yes, sir.
in week 1 maybe. Let me open this.
It's a module 1, I think, sir.
Okay, let me check this. Subthreshold slope. I remember there was a GIDL slope, but subthreshold slope.
Yes, sir, GIDL. Yes, sir.
Oh,
That's it.
okay, that one. So, okay, let me open this. Okay, yeah, okay, so the thing is like what we usually expect is if we are operating at if the gate voltage is something less than the VTH, then there won't be any current conduction through drain to source, right?
Yes, sir.
But when we go on scaling down the feature size from, let's say earlier it was 180 nanometer, then we go on reducing it till let's say 22, 28,
14
yeah, 14 or 7 nanometer. So then
Yes, sir.
many other subthreshold effect they start to come into picture. So one of them is this subthreshold leakage thing. Okay,
Slow.
so yeah,
Yes,
so
sir.
in that one what happens is like even if you are applying a VGS value which is below your VT, so it is, let's say this is my VGS and this is my, okay, this is my log ID, okay, and if this is my VT, then what is going to happen is, so I would have earlier assumed that exactly at VT it would go to 0, right? Okay,
Yes, sir.
but that does not happen, but it goes through a value like this. Okay, so
Yes,
this
sir.
is some finite value of current that is still present. Okay, and it will go on and on, okay, till it reaches a point called GIDL,
Yeah.
that is gate induced drain leakage. Okay, but then after this point what happens is there is a sudden jump, and this point is the, yeah, GIDL point.
Why that happens, sir, means
So okay, that will go deeper into the device physics side, so that is we are not really bothered about why it happens, but we just need to know that it happens, that even if we go on decreasing the VGS, there will be a point after which there can be a sudden jump in the current. Okay, so the why part, it will be better answered in a device physics course which deals with the physics that is behind the MOS transistors. Okay, and because of this thing, it actually encourages us to move to FinFETs. Okay, so so FinFETs, they are able to bring this particular thing down.
Okay, sir.
Okay, so yeah.
If we decrease the subthreshold swing, is it effect on the driving current, sir, on current?
Okay, so if we decrease the subthreshold, how are you planning to decrease the subthreshold leakage? By increasing the threshold?
Try to decrease the off current, sir. If we decrease the off current, it will decrease the subthreshold swing.
Correct, yes.
If we try to decrease the off current, is it affect the on current, sir?
No, but it will affect the speed of the transistor's operation, because the way usually it is done to decrease the I off is by increasing the VTH.
Yes, sir.
Okay, so if you increase the VTH, then it means, so earlier let's say it was switching at let us say 0.3 volts. Okay,
Yes,
so
sir.
now you increase the VTH to 0.4. So whenever you are going to switch, let's say you are linearly increasing the VG value, so it means you need to wait for delta time more in comparison to when you are doing for 0.3. So the charging discharging will now take time, so it results in a higher delay. But the trade-off means the benefit that you get is, so in the off condition, the subthreshold leakage part will be less.
Sir, without increasing the threshold voltage, can we decrease? By decreasing the gate capacitance, can we decrease the off current? Means if we decrease the gate capacitance, then the discharging time will decrease.
Correct.
So,
But
is it possible to decrease the gate?
Okay, then if you want to decrease the capacitance part, then it means you are planning to go into like lesser size of transistor. But if you decrease the size of the transistor, then it means that you are going to increase the resistance of the transistor.
What it means, sir, means resistance.
Yeah, so any transistor that is present, and like if you say the drain and source terminal are connected, so then it will have a resistive behavior, right? So just because of that reason, you remember whenever we were having stacks, so and we were saying that so this will offer some resistance R, and we need to scale the transistor up so that this resistance goes down.
Yes, sir.
Yeah, so
what if we do not means if we don't decrease the size, and if we insert any negative capacitance material at the gate terminal, is it possible?
Yeah, so exactly. So if you go into the device physics side, and if you have some innovations in that direction, like negative capacitance and those things, but yeah, so maybe you can do that, but it will have other additional effects as well. So that thing is not
on current, sir?
Not only on current. So here in whatever circuits we are drawing, we are not considering loops and all. Okay, so let's say I'm creating something which has a negative capacitance, as you mentioned, or something, but it is present in a loop. Okay, so there is a possibility that it can go into a positive feedback, and it will make the circuit unstable. So there are few additional things also we need to consider before means doing those things. But yeah, so this is, I think, out of this particular course's scope. But yeah, I think
Is it advisable, sir, for using the negative capacitance or?
I mean, personally, I haven't used any negative capacitance in any of my designs, but um, yeah, negative resistance is sometimes used, but negative capacitance I haven't. Means exactly what do you mean by negative capacitance when you mention that?
Capacitance means if we increase the voltage, then charge needs to decrease, sir.
Oh, okay. In that way, yeah, it can happen,
Sir.
right? Like if you are holding one end of the capacitance at a higher voltage, and the other end is connected to this thing. So it means if you are going on
Yes, sir.
increasing the charge, then the voltage difference will get reduced.
Yes, sir.
Yeah.
Then the off current will decrease, no, sir. Means if decrease the effective capacitance at the gate terminal, then charging and discharging times will decrease, no, sir.
Okay. Yeah.
Then
Yeah.
if discharging time decreases, then off current will decreases.
Yeah. Yeah. That is one thing that.
But
Actually, we also need to think about what can it affect. Um, what can it affect?
yes, sir. That's my doubt. Yes, sir.
Oh, okay. I think.
If we
Yeah.
if if we decrease the discharging time, then charging time also decreases. Is it decreases the charging time?
No, that will only happen if you are like reducing the VT. Okay. Otherwise, each time when you say that you have a capacitor, you need to again recharge it to that particular value. Isn't it?
Okay, yes, sir.
Okay. So your assignment deadline, is it tomorrow?
Yes, sir. Yes, sir.
Oh, okay.
Yes.
Okay. Yeah.
Sir, if we find out, sir, in that
Your voice is breaking. Can you repeat once again?
sir, in a circuit, if we have a NOT gate followed by a NAND gate, sir,
Huh.
am I audible? Hello.
Hello.
Sir, I'm audible. So,
Can you repeat your question?
hello.
Huh. Yeah.
Sir, in a circuit, if NOT gate is followed by a NAND gate, sir,
Okay.
and if the same circuit is in the same circuit, if we replace NAND by NOR gate and we provided the same output capacitance for the NOT gate, sir, inverter,
Okay.
then how resistance affects, sir, means resistance of the NAND gate and NOR gates.
So you are saying something like this.
How means if we provide the same output capacitance for the inverter, is there any effect takes place by the resistance of the NAND and NOR gates, sir? Input resistance of the NAND and NOR gate.
No, I have never thought about it, but yeah, I'll give it a thought, and if I come across anything, I'll let you know in the next session.
Okay, sir. Means my doubt is if the input capacitance of the NAND and NOR gate is same, but the input resistance is not same, then how will the delay affect? Means
Okay, I have never thought considering the input resistance part, but actually, yeah, you can try it out using the Elmore delay method.
okay, sir.
Okay, I think yeah, that can be done.
Sir, if we consider like that, uh, which resistance we should consider, sir, means pull up resistance or pull down resistance?
That depends on whether the output is rising or falling.
Okay, sir. Means rise delay and fall delay will be difference.
Yeah, if it is different. If it is same, then it doesn't matter, right?
Yes, okay.
Because for delay we take TP-LH plus TP-HL by 2.
Yes, sir.
So yeah.
Okay, sir.
Okay. Yeah. Okay.
Okay. Thank you.
Yeah.
Okay, sir.